All right, today we're tackling something that is both brilliantly simple and, honestly, kind of mind-blowing. We're talking about how we can literally reverse the flow of nature to get fresh water right from the sea.
You know, it's a question that feels almost like a riddle, doesn't it? We're surrounded by all this water, but most of it is completely useless to us. The secret, it turns out, is to first understand a fundamental process of nature, and then, well, figure out how to outsmart it.
Okay, so before we can get to the solution, we have to get our heads around this fundamental natural process called osmosis. You've probably heard the term before, but this is the science that really makes this whole thing tick.
All right, let's just imagine this U-shaped tube for a second. On one side, the left, we've got pure water, and on the other side, the right, we've got a saltwater solution. Now that barrier you see right in the middle, that's the star of the show. It's a special filter, a semi-permeable membrane, and it's super picky about what it lets pass through.
So, here's the key difference, and it's super important. The pure water on the left, it has a really high concentration of water molecules. The salt water on the right, though, has all those salt particles taking up space, which means it has a lower concentration of water molecules. And if there's one thing you need to know, it's this. Nature is always trying to find balance.
And that relentless drive for balance, that's what we call osmosis. It's simply the natural tendency for water to move from an area where it's crowded to an area where it's less crowded, trying to even things out. And it goes right through that membrane, which, remember, stops the salt but gives the water a free pass.
So, what's the result? Well, the water molecules do what comes naturally. They flow from the left side over to the right side, trying to water down that salty side and create the balance we were just talking about. And you can actually see it. The water level on the right has physically gone up. That's osmosis right there in front of you.
Now, that rising water level, it actually creates its own force. It's like nature is pushing back. And this force, it has a name, and it's the next big piece of our puzzle here.
That force is called osmotic pressure. And here's the best way to think about it. It's the exact amount of pressure you'd have to apply to that salty side to stop the water from flowing in. It's the pressure that perfectly counteracts or balances out the natural pull of osmosis. And this isn't just some abstract idea. It's a totally measurable force. The main takeaway here is pretty simple. The saltier the solution and the higher the temperature, the greater that osmotic pressure is going to be. Basically, the harder nature pushes.
So if we know the exact pressure needed to stop osmosis in its tracks, a really interesting question pops up. What happens if we apply even more pressure? And this, my friends, is where the whole ingenious solution comes into play. Right here, you can see we're applying an external force. We're pushing down on the saltwater side with a force that is stronger than the natural osmotic pressure. We're not just stopping nature, we're literally overpowering it. And this, right here, is called reverse osmosis. By cranking up the pressure past that natural osmotic point, we literally reverse the flow. So instead of water moving into the salt water, we force pure water to move out of it. So let's just break it down into 3 really simple steps. First, you've got your system, with the salt water separated by that special membrane. Second, you apply external pressure, more pressure than the osmotic pressure is pushing back with. And third, what happens? The direction of the flow flips and pure water gets squeezed out of the solution. And this is really the so what of it all. This exact process is how huge desalination plants take ocean water and turn it into fresh drinking water for entire cities. But it's also the very same principle at work in some of those high-end water filters you might even have in your own home. Okay, so let's zoom out for a minute. We've seen what osmosis does, right? But to really get why it happens, we need to look at the 2 fundamental forces that are basically running the show for all water molecules. You know, at the very heart of all this are these things called intermolecular forces. It's just the invisible push and pull between all the little molecules, and that constant dance is what dictates pretty much everything a liquid does. It's like the fundamental rule book for their behavior. The 2 big players here are cohesion and adhesion. Cohesion is the force of attraction between molecules that are identical, so water sticking to water. Adhesion, on the other hand, is the attraction between molecules that are different. Think of water sticking to the side of a glass. And this constant push and pull between molecules, it explains way more than just osmosis. It's the reason we have surface tension, which is what lets little insects walk on water. It explains viscosity, you know, how thick or runny a liquid is. And it's also responsible for capillary action, which is how water can climb up a narrow tube, seemingly defying gravity.
It's amazing how it's all connected.
So we started with a pretty simple question about salt water and ended up uncovering the fundamental forces that govern all liquids. From a tiny droplet on a leaf to our entire global water supply, it's all about understanding this flow, and sometimes knowing how to reverse it. So I'll leave you with this final thought. Now that you know the rules of osmosis, where else in the world do you see them at play?